there are just some, let's say, issues with the methodology. So in laboratory conditions, we usually stick to constant power trials, so we have time to exhaustion trials. That means the rider sits on the ergometer, we have a constant power output, and he's cycling as long as he sustains the given power. So we have an open-end test. Is this validly ecological valid? Yes or no? Yeah, we'll see later. And under field conditions, we usually use time trials. So we give them a fixed distance, that's usually used in running, or we give them a fixed duration, which is usually used in cycling. And those time trials really reflect real-world exercise, real-world competitions. Another main disadvantage of these time-to-exhaustion trials is that these time-to-exhaustion trials have a lower reliability than the time trials have. So, on the one hand, we have the laboratory test with a lower reliability. On the other hand, we have the field test with a higher reliability. So, our research question was, are time-to-exhaustion trials showing a significantly higher standard or error of the estimates than the time trials do because they have the lower reliability? Just a general overview of differences between laboratory and field test. We have not shown any differences in the estimates of critical power between the conditions, and also in critical speed in running. There was a study published years ago by Andy Galbraith who didn't neither find any significant differences in the estimates of critical speed. So we can compare those two estimates of critical power in laboratory and field conditions. But what about the standard error of the estimates? What did we do? We assessed critical power using 3 mathematical models. We used the nonlinear hyperbolic power versus time model. We used the linear work versus time model, and another linear model was used, the inverse model power versus the inverse of time. The standard error of the estimates of the regressions were calculated using GraphPad Prism software package, and we calculated the absolute standard error of the estimates and also the relative standard error of the estimates. Oops, wrong direction. So now, our results. We used a Wilcoxon-signed rank test as our data was not normally distributed, and also we had a rather small sample size with just 10 participants, and results presented as the median values and the range from minimum to maximum. So what did we find out? We found no significant differences between the conditions, so no differences in the standard area of the estimates, not in the relative and not in the absolute values. So we had huge differences between the models, especially in laboratory. So the models produced not significantly different standard error of the estimates, but they tended to produce different standard error of the estimates. And when we have a look at the ranges, so some of our cyclists really performed very, very well in laboratory, under laboratory conditions, but some of them, if you see here, 16% or even 11% performed quite worse under laboratory conditions. And nearly the same applies for the results under field conditions. So we have a range from 1.4% up to 3.1%, and also the range from about 1% up to more than 10% in the the relative values of the standard error of the estimates. Now we see the box plots. We have one outlier here in laboratory when using the linear model work versus time, and we see the medians from the box plots, and what we can see is that the standard error of the estimates don't show that much differences between the models under field conditions, but we have known significantly differences between the models in under laboratory, but they tended to be differently. And now, just to highlight some individual results, we have the hyperbolic model here, linear work versus time model, and the inverse model, power output versus the inverse of time. So we have a good fit for all models. However, if you have just a look at the coefficient of determination, the R-square differs between the models and also clearly differs between the conditions. So what we found out that the standard error of the estimates is not significantly different between time to exhaustion trials and time trials, and the reliability, the lower reliability of the time to exhaustion trials has no effect on the standard error of the estimates, as we found no significant differences. We have just other standard error of the estimates values from another unpublished study from Bettina. She found lower standard error of the estimates in her study, but she also found significant differences between the laboratory time to exhaustion trial and the time trial under field conditions. So in her study there have been significant differences. In our study there were no significant differences, even though both studies used experienced cyclists, and the Pmax values, the VO2 max values were apparently the same in our study. So another study we have currently under review, assessing critical speed, we found significant differences in the standard error of the estimates between laboratory time to exhaustion trials and field time trials, but with this cycling study we didn't find any differences. So to conclude, no significant differences between time to exhaustion and time trial. However, under field conditions the standard error of the estimates were smaller, and also the differences between the models were smaller. And according to these results, we could suggest also the time to exhaustion trial in under laboratory conditions, but ecological validity is much lower with the time to exhaustion trial. So new results, still unpublished results, indicate that we should prefer also in laboratory the time trial to elevate the ecological validity. Thank you for your attention.